Hi, thanks for watching. My name is Zhiyuan, and I'm going to present Igor. This is a joint work with Ahmad and Matthias from Hexhive at EPFL, and Chao Zhang from Tsinghua University. In recent years, fuzzing has developed rapidly. A large number of bugs have been discovered by fuzzing. However, the fuzzing technology has also brought a new problem for security testers. That is, too many crashes are discovered, while manual debugging process is often time-consuming. It is neither realistic nor necessary to analyze crashes one by one manually. The number of crashes often far exceeds the number of bugs. In order to save developers time, we urgently need to deduplicate crashes. A large number of crashes caused by different bugs should be divided into multiple groups according to the root cause, and each group represents a unique bug. After grouping, developers can perform manual analysis for only one or a few crashes in a group, which greatly improves the efficiency of developers to fix bugs. Therefore, the challenge addressed by our research is, given n crashes, how do we group them into m unique bugs? In response to this problem, let's take a look at the existing crash deduplication method. First of all, it is a common practice in the industry to group crashes according to the different call stacks at the time of the crash. If the stack hash are the same, they are grouped together. The method is fast but lacks precision. For example, in this code snippet, before the program enters the switch branch, due to an overflow, the VPTR pointer was overwritten with an illegal address. Therefore, as long as the VPTR pointer is dereferenced, the program will crash. We see that there are opportunities to use VPTR in lines 3, 7, 11, and 12 in the example. So they will have different call stack hash when the crash is triggered. If we group crashes according to the stack hash, we will divide them into multiple categories, but in fact, their root cause are the same. We call this type of error that classifies crashes of the same bug into different groups as type 1 error. Type 1 error is also the main challenge of crash classification at present. Since using call stacks is not reliable, researchers have proposed a second method. They group crashes by comparing the crash address and treat the same crash address as the same bug. This method has one key limitation. Different bugs may be grouped into the same category, which we call type 2 error. For example, there are two overflow functions, overflow 1 and overflow 2. These two functions will cause stack overflow, and both of them will crash when calling memory copy. So the crash address is the same, but obviously there are two different bugs. If we group the crashes according to their crash address, they will be grouped together, meaning one bug will be lost. Of course, in recent years, there have been some academic papers that classify crashes based on timed analysis, program slicing, and symbolic execution. The common problem is that they are usually not practical for real-world programs due to computational cost or state explosion. In response to the above problems, after analyzing the massive crashes found in the long-term fuzzing test, we got the following conclusions. First of all, the existing classification method have over or under classification problems, and the over classification problem is the most common. Secondly, there must be a unique trigger method for each vulnerability. and a large number of new paths discovered by the fuzzing test are actually independent of this triggering path. For crashes of the same root cause, their control flow graph have much more higher overlap. Through the similarity comparison of control flow graph topology, we can group crashes of the same root cause together. Therefore, our idea is, since the duplication is caused by paths that have nothing to do with the availability triggering, we will remove these irrelevant path segments. Removing the irrelevant path segments can be regarded as a form of denoising. After that, we will cluster based on the graph similarity to achieve the deduplication. In summary, the overall workflow of our system is shown in the figure. Given a large number of crashes generated by fuzzer as the input, we first process the data to reduce the subsequent computational overhead from the number and the scale of a single crash, and then use Igor fuzz to minimize these crashes. After recording the execution traces for each minimized PoC, our graph analyzer began analyzing the trace to calculate their similarity. The cluster builder takes the similarity matrix as input to get clustered crashes as the final result. Let's talk about how to minimize the PoC on the control flow. We designed Igor fuzz to do that. The goal of Igor fuzz is to find the shortest bug triggering path. Our core method is applying minimum coverage fuzzing to prune those bug irrelevant paths step by step. The first is the seed retention strategy. We have proposed two rules. The first rule is to retain seed that can eliminate edges that have been executed. For example, the red dashed line indicates the path executed by the original crash. If we found the green path, the path it executed is a subset of the original path. Edge 2, 3, 4 are removed, so we will keep it. However, during the fuzzing process, it is not always possible to find such an ideal path. It happens to be the path of the subset, and more often it is the blue dashed line. That is, some edges are deleted and some new edges are introduced. We also keep this type of seed in the queen, because it can eliminate at least one common edge. It has value for subsequent mutations. Just deleting edges is not enough. Sometimes, an edge cannot be pruned immediately. Considering loops, an edge needs to gradually reduce its execution times until the final deletion is successful. Therefore, in the process of mutation, we not only monitor the deletion of edges, but also the change in the number of edge hits. If it is found that a certain seed does not remove any edges, but the number of edge hits is reduced, we will keep this seed as a seed of interest. In addition to the seed retention strategy and the seed selection strategy, we also have a specific design for the energy scheduling strategy of the seed. To prevent the discovery of new bugs in the fuzzing process from causing inaccurate classification result, we also propose a seed selection strategy for the final output of Igor fuzz. This picture shows the minimization result of Igor fuzz. Red nodes indicate path segments executed by the original crash, but later pruned by Igor fuzz. The green nodes indicate new paths introduced by Igor fuzz. The result shows that Igor fuzz can eliminate a large number of bug-irrelevant paths. Taking crashes as input, we get minimized crashes from Igor fuzz. We can construct their control flow graphs and calculate their graph similarity metrics. Passing these metrics to cluster, we can get the final result, namely groups or crashes that are clustered together and correspond to the same bug. We implemented Igor fuzz based on the crash mode of AFL++ and use pin to record the execution trace of the crash. We use GraphQL to calculate the graph similarity and skk-learn to do the clustering. Our code is available in our repo. In order to test the accuracy of the group result of our tools, we also designed and built a benchmark. First of all, it includes a large number of crashes, and each crash is labeled according to its root cause. Second, it only uses real-world software, and this software are commonly used in fuzzing tests. Third, each software contains multiple vulnerabilities. We first collect the patches of these vulnerabilities from their repositories and patch the vulnerable programs with them one by one. If a crash no longer causes the program to crash after applying a certain patch, the root cause of the crash is considered to be the bug fixed by the patch. Of course, sometimes developers will also release insufficient patches or duplicate patches. Therefore, in order to improve the accuracy of labeling, we perform further confirmation manually. This is why our benchmark contains 51 CVE, corresponding to only 39 bugs, because we found duplicate patches during the manual verification. Our benchmark is also open sourced. Follow-up researchers can use the benchmark we provide to further study the problem of crash deduplication. Next, introduce our evaluation. Let's first look at the performance of Igor fuzz. We use bitmap size to represent the number of edges that the crash has executed. This picture shows the curve of the bitmap size of crash over time during the operation of Igor fuzz. First, we can see that the bitmap size decreases monotonically over time. Second, we can find Igor fuzz is fast. Most crashes can finish its minimization within 150 seconds, and their edges can be pruned sharply. This indicates that a short timeout for coverage decrease fuzzing is sufficient. Next, we want to present what effect does minimization have on the cluster. This figure shows the cluster result if we do not use Igor fuzz to minimize the crash. We can intuitively feel that the crashes of the different root causes are mixed together, and there is no obvious interface. It is difficult to separate them whether by visual observation or using clustering algorithms. Next, let's take a look at the effect of using our tool to minimize the execution trace. As shown in the figure on the right, after the reduction, the crashes of the same bug are more closely grouped, and the crashes of different bugs are more clearly separate from each other. The figure shows clear clusters, which can even be directly distinguished by the eyes. According to our experiments, if we do not use coverage decrease fuzzing, we group all crashes belong to 4 bugs into 9 categories. But after the minimization through coverage decrease fuzzing, we can cluster the crashes into 4 groups accurately. Finally, we show the comparison between Igor and the existing crash deduplication method. Here, we have selected a few comparison objects, which are based on the crash address and call stacks. For example, there are 3 bugs in PDF images, we have 410 crashes before deduplication. If we group them according to the crash address, they will be divided into 12 groups. If we group them according to the call stack, they will be divided into 23 groups. But Igor can group them into 3 groups. We can also see that the classification result of Igor is always better than other tools, especially when the software contains a large number of vulnerabilities, such as XML lint contains 1,581 crashes caused by 8 vulnerabilities. If we classify according to their call stack, we will have 901 groups. If we group according to the crash addresses, we will get 25 groups, but Igor can group them into 14 groups. We also perform an extended study on type 1 and type 2 errors. Details can be found in our paper. Finally, let's conclude. Fuzzing is indeed very fast in discovering crashes, but the resulting large number of crashes makes it challenging for security analysis to analyze them individually. Therefore, before handing over these crashes to the developer, we should first group them and clarify the number of bugs behind the crash, so that these crashes become more valuable for the developer. Our findings are as following. Reducing the program execution path or crashes improve the similarity of similar crashes for the same bug. Using topological structure similarity of the control flow graph to cluster crashes achieve good result. Our tool successfully divides 254,000 crashes caused by 39 vulnerabilities into 48 categories, achieving significantly better result than existing tools. Thank you.